The railway track manufacturing is fast developing these years as well as the railway track construction technology. The process of building railway tracks has been evolved in the late years. The gradual development is changing with the upgrade of railroad tracks for sale. The old way of track construction mainly counting on numbers of workers using simple tools. Now, things are quite different since the innovation and application of modern railway construction machine. With different types of modern machines, the job gets done much easier and saves labor and time, especially when it comes to building a high-speed rail with lengthening rails, one section 500 meters long or more. The efficient work of construction is essential. Process of building railway tracks. Logistics preparation. A logistics station is chosen as near as possible to the railway construction site. All the track material needed for railway construction is stored there. Concrete sleepers have been strategically placed. These sleepers are later loaded onto the empty tie cars and the loaded cars are moved to the track construction machine for installation. On another occasion, rails are installed on the sleepers advanced here and later being laid on roadbed by machine. Bottom ballasting. Theoretically, the rails should be laid on the pre-paved and tamped track bed, but due to a large amount of ballast required per kilometer of the railway, up to 2,000 cubic meters per kilometer, the railway itself must be used for transportation to reduce freight and shorten the construction period. Therefore, other means of transportation are generally used first, and only a small number of ballast, or even just 2 layers of ballast under the rails, are laid. Trains are used to fill up the ballast as soon as possible after the tracks are laid. The ballasting work includes many operations such as transportation, unloading, spreading, lifting track, lining the track, tamping, and ballast bed shaping. Among them, the transportation and unloading of ballast are mostly carried out by special automatic ballast unloading vehicles. For other operations, most countries use ballast machines with comprehensive work performance. Sleepers and tracks laying. Normally, sleepers are laid first and railway tracks are laid next. However, they can be laid together at one time if the rails and sleepers are combined previously. Let's take a look at how concrete sleepers are made. These workhorses are actually cast upside down in long molds that can hold several sleepers at once. Before the concrete goes in, they strategically place panroll clip bases or other fittings into the mold. Strength is key, so we also install pre-stressed steel reinforcing bars. Once everything's in place, The concrete is poured and left to cure for several days. After curing, the long form is removed, and individual sleepers are cut using specialized equipment. By the way, you can usually find the manufacturer's logo and date stamp on the bottom of the sleeper, a handy bit of information. Now, there can be some variations. Sometimes, sleepers are cast with built-in conduits for electrical wiring, or special features to accommodate guardrails. There are also two main production methods, long line and short line, each with their own pros and cons. Once they're produced, numerous companies around the world supply these concrete sleepers. They typically arrive on site in neat stacks, separated by lumber to prevent damage. The actual laying process can be done by hand or with the help of various specialized sleeper laying machines. One typical track construction machine is composed of a caterpillar, the main control operation, a self-propelled gantry. It can lay new sleepers, thread new rail, clip the rail to the ties. The new rail, which was previously positioned along sides of the way that threaded to the rail guides located at the front of the unit. The main control operation monitors the conveyor systems and the sidewalk mechanism. The self-propelled gantry keeps ties applied to conveyor systems. The gantry moves to the tie receiving conveyor, deposits ties, and returns to the tie supply car for another load. After being deposited by the gantry, the ties moves by a conveyor system through the ties drop area. The ties are discharged from the tie placement mechanism and are precisely spaced on the roadbed. After the rail passes through the rail guides, it is guided into a gauging station. The final placing of the rail to the ties is controlled by an operator who guides the rail onto tie seat. The clipping is carried out by nipper clipper mechanism near the rear of the machine. Alright everyone, let's talk about heat welding, also known as thermite welding. This is a technique widely used to connect railway tracks, creating those long, seamless stretches we all know. Here's how it works. The magic ingredient is thermite, a mix of aluminum powder and iron oxide, inside a crucible. This mixture undergoes a super hot, self-sustaining reaction. We're talking temperatures reaching around 1,500 degrees Celsius. This reaction creates molten iron, the good stuff that binds the rails together, along with some waste material called slag. So why thermite welding? It all boils down to a smoother, more enjoyable train ride. By creating long, continuous rails, reduce those annoying bumps and jolts. Plus, these welds are incredibly strong and long-lasting, minimizing maintenance needs. Another perk, thermite welding can be done in tricky locations, like bridges and turnouts, where other welding methods might not be so easy. Trains are a cost-effective and efficient mode of transportation for both goods and passengers. They can carry large volumes of cargo over long distances, making them crucial for industries such as manufacturing, agriculture, and retail. Similarly, trains offer a reliable means of commuting and long-distance travel for people, reducing congestion on roads and decreasing travel times. The development of railways has often been synonymous with economic growth. Railways facilitate trade by connecting regions, enabling the movement of goods and resources. They also stimulate industrialization by providing a means to transport raw materials to factories and finished products to markets. In developing countries, the expansion of railway networks can lead to increased investment, job creation, and improved access to markets. Trains running mile after mile put high demands on their wheels. Meeting their requirements on dimensional tolerances and surface quality is essential, both as a matter of safety but also in terms of comfort for the passenger. Producing finished wheels involves a manufacturing chain including different forming processes, metal cutting, and testing. Early train wheels were made of cast iron. Today, they are typically cast or forged steel, treated for specific hardness. Manufacturing involves machining the wheels to a standardized profile after the initial casting or forging. The materials used in train wheel manufacturing play a vital role in determining the performance, durability, and safety of the wheels. The most common material used in the production of train wheels is steel, but other materials are also used depending on specific requirements and applications. Steel is the preferred choice for train wheel manufacturing due to its high strength, durability, and resistance to wear. These properties are essential for train wheels, which are subjected to heavy loads, high speeds, and continuous friction with the rails. There are various types of steel used in train wheel manufacturing, with a specific composition and grade depending on the requirements of the application. For example, high-speed trains may require a different composition of steel than freight trains, which carry heavier loads. Manufacturing process of train wheels. The manufacturing process of train wheels involves several key steps to ensure their quality, durability, and performance. These steps include material selection, casting or forging, heat treatment, machining, and quality control and inspection. Material selection. The first step in the train wheel manufacturing process is selecting the appropriate material based on the specific requirements of the application. As mentioned earlier, steel is the most common material used for train wheels due to its high strength, durability, and resistance to wear. However, alternative materials such as cast iron and composite materials may be considered for specific situations. Forging. Forging, on the other hand, is a process in which the material is heated to a high temperature and then pressed or hammered into the desired shape using a die or a press. Forged train wheels typically have higher strength and durability compared to cast wheels, as the forging process aligns the grain structure of the material, providing better mechanical properties. Blanks are heated in a rotary kiln before compression forged. The center is then punched out and the profile is roll-formed. A bending process gives the wheel its final shape, and then the wheel rim is chilled in water, thus hardening it. Finally, the wheel's mechanical properties are tested to ensure the wheel is ready for further machining. To achieve required dimensions and surface quality, the hub, web, and rim on the wheel are machined. Round inserts are combined with over and under coolant for best performance and chip evacuation. Non-destructive testing ensures the wheel surface meets the requirements on quality and tolerances. Then it's mounted on the axis, installed on the train, and ready for use. The manufacture of train wheels is a complex process. In the production process, quality inspection plays a vital role because the quality of the wheels directly affects the driving safety and operating costs of the train. In the field of wheel manufacturing, automation of the entire quality inspection process has gradually become a trend. In the current wheel manufacturing process, there are two main inspection methods: offline inspection and online inspection. Offline inspection means that the finished wheels are disassembled from the production line and then inspected. This approach can cause damage to the wheels and requires additional time and cost. Online inspection is an uninterrupted inspection during the production process, which can effectively avoid potential damage and waste of time and cost caused by disassembly. The automation of the entire quality inspection process relies on a variety of technologies and equipment, such as laser sensors, digital image processing technology, non-destructive testing technology, etc. These technologies and equipment can help wheel manufacturers quickly and accurately detect the size, shape, quality, defects, and other indicators of wheels, and can also greatly improve inspection efficiency and accuracy. Take laser sensors, for example, which measure as the wheel rotates to ensure accurate measurement data. Non-destructive testing technology using digital image processing technology can detect subtle defects on the wheel surface, such as cracks, burrs, bubbles, and other problems, greatly improving the detection accuracy, and the detection speed is also very fast. The automation of the entire quality inspection process can make full use of digital technology to provide support for inspection, such as using computer vision systems and computer control systems to process and analyze wheel data. This not only optimizes the wheel data processing process, but also enables real-time monitoring and timely correction of wheel data. In today's era of rapid changes in industrial production, the manufacturing process of train wheels has realized full process automation, and its manufacturing accuracy has reached the micron level. This highly automated production process can greatly improve manufacturing efficiency and quality, and reduce errors caused by human factors. After a period on the tracks, wheels need returning. The train rolls into the machine shop, where every flat spot, flange deformation, and crack is removed until the wheels are reset to their former standard, ready for another cycle. Regular intervals. Train wheels are inspected at predetermined intervals based on factors like mileage, time, or even condition monitoring systems. Visual inspection. This involves looking for wear, cracks, or other damage on the wheel tread and flange. Measurement. Instruments are used to measure key parameters like wheel diameter, flange height and width, and wheel set width. These measurements are compared to established safety standards. Train wheels wear just as car tires do, and they need to be checked regularly. When the wear reaches certain limits, the treads either have to be reprofiled to the correct shape or the wheels replaced. Reprofiling wheels is a slow and expensive process, but train and wheel design and maintenance has improved considerably over recent years, reducing the periods between visits for reprofiling. Even so, there are still persistent cases of railways running into unforeseen or unusual wheel wear problems, and the wheel/rail interface still needs a lot more research before it is fully understood. Wheels on a bogie or wheels on a single vehicle must be reprofiled within limits compared with each other. For example, a standard set for one type of passenger coach says that wheels in the same bogie must not vary in diameter by more than 5 millimeters. Wheels under the same coach must not vary more than 10 millimeters on different bogies. The most modern vehicles might require a tolerance as low as 3 millimeters. When wheels which drive a speedometer are reprofiled, the speedometer will have to be adjusted to compensate for the difference in wheel diameter caused by the reprofiling. Some modern wheels lathes are designed to turn both wheel sets on a bogie at the same time. These double-headed lathes have developed as a result of electronically controlled AC motors, which require that the motors in the same circuit turn at the same speed so as to match the inverter frequency. This makes it essential that wheel diameters with motors within a traction power circuit are equal. Although it might seem obvious, the roundness of wheels is important, especially at very high speeds. An eccentric wheel can cause extreme loads on the wheel, axle, bearing, and suspension, leading to failures. An unround, out-of-round, or eccentric wheel is alleged to have led to wheel tire failure of a German ice at Eschede in 1998, causing a high-speed crash with heavy loss of life. The wheel is alleged to have had an eccentricity difference between major and minor axes of the ellipse of 1.1 millimeters against a limit of 0.6 millimeter. Wheels are often damaged by skidding during braking. Skidding, called sliding, causes a flat patch, called a flat, to wear on the tire, and when the wheel begins rolling again after a slide, the familiar tap, tap, tap of the flat will be heard. Overheating during braking can also damage a wheel, as shown in the next photo. Even if wheels, by some lucky combination of circumstances, do not wear significantly, reprofiling to remove work-hardened metal is likely to be needed at around 1 million km. Otherwise, martensite fragments can rot out of the wheel tread, leading to the type of damage shown in the photo above. This damage can also be caused by local overheating during skidding and slash or braking.